Good afternoon, this is Stan Forrester. We're covering Chapter 8, Rotational Kinematics for Physics at Indian River State College. So let's go ahead and let's get started. Okay, so first of all, rotational motion. Okay, we're going to be talking about angular displacement. We're all familiar with linear displacement. If you go from, say, 5 meters back to 3 meters, your displacement is -2. Your final minus initial, 3 minus 5 is -2. And similarly, if you start at 5 and you end at 10, 10 minus 5 is 5. You changed your displacement by 5 units. Okay, obviously that's dependent on your coordinate system. But angular displacement works pretty much the same way with one exception. And that is that you can come right back around to your starting position. Okay, so let's take a look at our spinning disk here. I doubt very much anybody has a CD player anymore, but that is an ancient technology called a CD, or compact disc. In any case, there's a reference line here that we're going to call 0. This is our reference line here, so this is theta equals 0. We have a second reference line that we're going to call theta 1, which is our initial displacement, and theta with no indice, which is our current position. Okay, so the difference between these two, so take our final theta minus theta initial, that is delta theta. That is our angular displacement. The thing to keep in mind about angular displacements is they're measured in radians or degrees. In physics, there are advantages to having a unitless, there are no units of radians, okay, so you can plug them directly into equations and things of that sort, whereas degrees you have to convert it to radians before you can square them and things of that sort, okay? So, what is an angular displacement? Okay, we're going to, in terms of this compact disk, we have this edge, the rounded edge here on the circumference, that is S, that is an arc length. We have a radius, or a distance from the center. S over R, or arc length divided by the radius, that is your angular displacement. As a matter of fact, it is this, the units of radians are what make this true. If you wanted to measure your angular displacement in degrees, you'd have to have some kind of numerical conversion here. But say 3 units of length in arc length, which is almost all the way around, or about halfway around, divided by 1 meter radius, that would give you, well, 3 divided by 1 is 3 radians. Okay, full revolution is 2 pi radians. Now, a pi is just a little more than 3, so this is like 6.28 radians is a full circle. Okay, or 2 pi radians is equal to 360 degrees. And there's a conversion there that you can create if you wish. Okay, so 2 pi r, that is the circumference of a circle. The radius, remember this is the arc length, 2 pi r divided by r, and you're just left with 2 pi radians. Okay, so the units cancel out. There are no units in radians. It's sort of a fictitious unit. We just say radians so that we know we're talking about an angle. Okay, and here's our definition of angular displacement. This is final minus initial. Deltas are always final minus initial. So here's our final final angular position minus our initial angular position, and the difference between those two, that's your displacement. Okay, just like we had average and instantaneous linear velocities and accelerations, we have the same thing for your angular quantities. Your average angular velocity is your angular displacement divided by the elapsed time. Okay, and we're going to use this funky W there, what's called omega, and a bar over the top that's going to be our average. That bar means average, so our average angular velocity is just the change in displacement, our angular displacement, over the change in time. Okay, and this is going to be radians per second, or sometimes just per second. All right. Okay, instantaneous angular velocity. I warned you before, we could let that delta t go to 0, and your average becomes your instantaneous, just like it does for instantaneous velocity. Okay, average angular acceleration is a change in angular velocity over a change in time. Okay, and again, the bar. And okay, the alpha means angular acceleration, the bar means average, and we simply have a difference or a change in angular speed, angular velocity over a change in time. Now we usually deal with constant accelerations. Okay, so our kinematic equations all said you had to have your constant acceleration. we're not going to deal with changing angular accelerations either. And so there's really no point in going to an instantaneous acceleration. Okay, and this is, units are radians per second squared. Right? I want you to take a look at all of these kinematic equations, and these are the kinematic equations. They just have funky letters. All right, so angular velocity is equal to initial angular velocity plus acceleration over time, angular acceleration over time. Notice how this is very similar to our linear kinematic equations. Okay, final velocity is equal to initial velocity plus angular acceleration over time. Okay, so they have very similar forms. They just changed letters. Okay, final angular velocity squared is equal to the initial angular velocity squared plus 2 times the angular acceleration over the displacement, angular displacement. And again, we have one of our base equations here. Our angular displacement is equal to our initial angular speed times time plus 1/2 the angular acceleration times time squared. All right. And then we're going to make that much more clear here. We're going to compare directly the rotational motion equations to our linear motion equations. And you can see that the forms are exactly the same because the mathematics is exactly the same. Even though they're describing very different quantities, like an angular speed is not a linear speed, all right? But mathematically, they're describing the same kind of relationships, and so they have the same forms. Now, if you're ever confused, here's a nice little table that helps you figure out what the parallels are. So theta is a displacement. It's an angular displacement. X is the displacement in linear motion. Okay, alpha is the acceleration, angular acceleration, and A is the linear acceleration. Okay, reasoning strategies. Okay, we're going to make some drawings. We're going to decide which directions are to be called positive and negative. Your text uses counterclockwise to be positive. Okay, write down the values that are given for any of the 5 kinematic variables. Okay, and you probably need about 3, but remember there's some key words in there, like at rest usually means that one of your speeds is 0. Constant velocity means that one of your accelerations is 0. Okay, verify the information contains at least 3 of those 5 kinematic variables. Then you're going to select the appropriate equation. When the motion is divided into segments, remember the final angular velocity of one segment is the initial angular velocity of the next. And keep in mind there may be 2 possible kinematic, 2 answers to the kinematic problems. If you have to use the quadratic equation, you will end up with, well, not you will, it's very possible that you'll end up with 2 different answers. Okay, let's talk about if you have, let's say we have 5 skaters in a row, okay? Now, since they're all on the same reference line, they're all going to have the same angular position. They're all going to have the same angular speed, all right? But we know that the motion of the outermost skater is going to be very different than the innermost skater, okay? The angular motion is the same, okay? But we're going to take into account these tangential velocities and tangential speeds, okay? So remember, your angular speed is the arc length divided by, angular position is arc length divided by the radius. But for each of them, as the arc length gets bigger, so does the radius. So the angular position stays the same. All right, your tangential speed, though, because he's going around, this outermost skater is going around in a bigger circle, he's going to be traveling faster. Tangential to the circle he's traveling in. So what exactly is that relationship? Okay, your tangential speed, or b sub t, is equal to the radius times your angular speed. Now notice the units here. Your radius is in meters, your angular speed is in per second, so this has units of meters per second. That's a speed. Here's your tangential acceleration. Tangential acceleration is equal to your radius times your angular acceleration. Okay, right-hand rule. If you want to figure out what's positive and what's negative, take your fingers, right hand, curl your fingers in the direction of rotation, use your thumb, and that gives you the direction of your angular velocity axis. Okay, lots of examples in the textbook. If you have a specific request, I will go over that, make a little video, post it, and until then, Make sure you review all of this prior to exam 3. Okay? Thank you very much.